Yes. Okay, let's get started. My name is Ashley Smith, and I will be presenting French press on behalf of Cary Academy. First, let's address the problem statement. We were asked to investigate, both experimentally and theoretically, the onset of turbulence and the mixing of fluids inside a French press coffee pot. To begin, we will start with some background information. French presses deal in fluid dynamics. Fluid dynamics is the study of fluid flow. Every fluid is different and will thus act uniquely depending on certain physical characteristics that I will return to in a bit. There are two very important types of fluid flow: turbulent flow and laminar flow. Turbulent and laminar flow appear in many forms and indeed form somewhat of a sliding scale, wherein a fluid can become increasingly more and more turbulent. But there are some marked characteristics of each. Laminar flow is much more predictable, and the velocity is constant at each point in time. Whereas in turbulent flow, there are many irregular fluctuations and the velocity varies in both magnitude and direction quite wildly. Our presentation will have two parts. The first is about our investigation into spheres. To begin with that, we'll talk about Reynolds number. Reynolds number is a ratio of the inertial forces in a fluid to the viscous forces, and it helps predict how a fluid is going to flow and whether it will be laminar or turbulent. Higher Reynolds numbers tend to indicate more turbulent flow, while lower Reynolds numbers tend to indicate more laminar flow. For some examples of that, on the top left, you see a Reynolds number of between 0 and 1, 10 to the negative second, in which the fluid is moving quite laminarly and is not being disturbed much by the sphere that is in the way. However, you see as it increases to 20, 100, and 10 to the 6th, it gets increasingly more turbulent, and these vortices that you can see, called eddies, form behind the sphere. Next, I'll talk about drag coefficient. Drag coefficient is a unitless number that represents an object's resistance to movement through a fluid. We derived our own drag coefficient by finding that mg minus the friction force in a French press would be equal to drag, and then we were able to set that equal to our drag equation and solve for drag coefficient. Now, we'll put the two pieces together. This is the Reynolds graph. On the x-axis, we have Reynolds number, and on the y-axis, we have drag coefficient. This graph was created by the physicist Osborne Reynolds in his experiment with perfect spheres going through various fluids and calculating Reynolds number and drag coefficient for each. And he was able to find that the fluid will become increasingly more and more turbulent as the Reynolds number increases. Our original hypothesis was that French presses would abide by these same rules. That takes us to our first experiment, which was to recreate Reynolds graph using spheres so that we could better understand how it worked. Our procedure was this. We found our viscosity, density, velocity, and the diameter and area of the plunger, as well as varying the force that we had, the mass that we had attached to the top of the French press. And we created an Excel spreadsheet to use the formula to calculate Reynolds number and drag coefficient. We also tested 4 different substances: acetone, glycerin, water, and isopropyl alcohol, because they all had very different viscosities. The graph that we found looked like this. It's scaled quite differently than Reynolds graph is, but as you can see, we have a very steep downward curve that reflects that of the beginning portion of the Reynolds graph, as you can see in the red square. We were not able to replicate Reynolds numbers over 10 to the 4th because that would require pumping a fluid at a very high velocity, which we were not able to achieve in this particular experiment. But nevertheless, we felt confident in moving forward to our second experiment, which was actually bringing the French press into the experiment and using an actual coffee ground to visualize the flow. First, let's consider some force diagrams. On the left, we have the plunger in a French press falling before it hits constant velocity in the fluid, in which mg is greater than the buoyant force. and the French press is accelerating, or the plunger is accelerating. And then on the right, we have a force diagram of the plunger as it is falling without a liquid inside the French press. And mg is greater than the friction force, and it is still accelerating. The procedure for this particular experiment was we recorded videos with different added masses to the top of the plunger, ranging from 0 grams to 60 grams. Then we used logger pro analysis to track the motion of both the coffee ground and the plunger, from which we could find the velocity of each and calculate Reynolds number and drag coefficient. Here are some examples of our trial comparisons. We have our 0 added grams to the top of the plunger on the left, our 30 added grams, and our 60 added grams. We collected a lot of velocity data from our experiments, and we thought that it would be a good idea to take the standard deviation of the velocities in each trial and set it equal to Reynolds number on the x-axis with standard deviation on the y-axis. We had originally hypothesized that this would result in a linear relationship because it made sense that as Reynolds number increased, the fluid would become increasingly more turbulent, and then there would be a larger range of velocities, and the standard deviation would increase. We did not find that this happened when we graphed our particular points. However, we think that this is due to the fact that a French press and the shape of the plunger is quite different than that of the Reynolds graph, which was derived from spheres falling through various liquids. A sphere is, of course, a very different shape than that of the plunger in a French press, which has a lot of very tiny holes, and thus would cause the liquids in the French press to act quite differently. In the French press, friction is not negligible, and so we were able to calculate the friction in our French press by creating a force diagram. We took the moment at which the French press is accelerating, or the plunger is accelerating through the French press without any liquids inside of it. We took a video of this, and we were able to find the velocity and then the acceleration in logger pro and plug it into our formula, which was friction force should be equal to mg minus ma. From there, we found our friction force, and we're able to account for it when we plugged it into our drag coefficient formula. Finally, with our numbers collected, we had our final Reynolds graph for the French press. On the x-axis, we have Reynolds number, and on the y-axis, we have our drag coefficient numbers. As you can see on the far right, we have a collection of points that look quite similar to the curve that can be seen in the Reynolds graph. And then we have our glycerin point, which is in what's called Stokes region, which is Reynolds numbers between 0 and 1. We also have, the arrow indicates that we also had additional points that could be found going in that same upward trajectory, but chose not to include them on the graph because we did not want, we wanted to highlight the fact that these numbers on the far right represent the left part, or the right part of the Reynolds graph.
1 minute.
So finally, for our conclusion and real-world application, we have shown that the more downward force applied to the French press, the more turbulent the fluid inside will be. In the instance of making coffee, the coffee grounds are not large enough to fit through the mesh of a real French press, but the water can fit through the holes and subsequently become turbulent as it is pushed through the holes. French presses abide by Reynolds graph, wherein the larger the Reynolds number, the more turbulent the fluid will be. However, we observed, as can be seen from the graph we created on the previous slide, that there is a slight shift in our French press Reynolds graph compared to the original sphere-derived one due to the different shape of the French press compared to that of spheres. Thank you very much. Okay.
1 minute.
Yeah, then ask about it.
This is my first question.
Okay. Time. Start.
Okay, so the opponent now has 12 minutes to engage in conversation with the reporter. You are not permitted to address the jury, but rather you should ask questions and guide the discussion. You may get started.
Can you please move back to slide 16?
Yes.
Maybe it's on slide 16. The slide with the Reynolds number?
Oh, our graph.
When you calculated the Reynolds number, what length scale did you use as a characteristic length scale?
So we use the diameter of the plunger in our French press.
When the flow is going through the individual holes of the mesh, do you think it still abides by the length scale of the diameter of the mesh, of the plunger, or do you think it would use a different length scale? And how would that affect the Reynolds number?
I would imagine that it would have similar results, but that the graph would be perhaps shifted slightly. We were not able to completely account for that, but diameters was what we felt was the best way to represent that dimension.
If the length scale was much smaller, for instance, the size of the individual mesh holes when going through the mesh, wouldn't that affect not only the Reynolds number and the drag coefficient, but also the way that the drag force is calculated?
Would you clarify your question a little?
I guess my question is, does the flow regime, laminar versus turbulent flow, affect the calculation of the drag force?
So drag force, I can show you up here. The velocity that is required in drag force is the velocity of the plunger. And so we imagined while working on this, as well as the diameter divided by 2 squared, so the radius of the French press, we had imagined that because we were just accounting for the diameter and the velocity of the plunger as it moved downward, the constant velocity, that it I'm sorry, could you repeat your question one more time? I want to make sure I'm answering it correctly.
I'm just wondering if when you're calculating the drag force, you assume here that it's the drag force on object in turbulent flow, which is calculated differently than an object in laminar flow. So I'm wondering if you considered how the changing Reynolds number would impact your calculation of the drag force.
So when we calculated Reynolds number, we took the mean velocity of the turbulent region. When looking at our graphs, what we often noticed as far as like total velocity values was that in the beginning, the velocities would be kind of everywhere. We'd have a point here, and then way up here, and then down back here. And then eventually, as you could see in the videos, the water settles and becomes more laminar eventually. And our velocity points would eventually even out into a much more discernible like line of sorts. And so we took the mean average, or the mean of the velocity values in that turbulent region where the velocities were moving all over the place, and that is what we calculated our Reynolds number with. So it was not a particular point, but an average.
I'm more worried about the length scale involved, since the length scales would shift depending on whether the flow would be in the holes of the mesh or in the diameter of the plunger, and how that would affect your calculation of the Reynolds number and the drag force. I understand that the velocity would be turbulent. Never mind, let's move on. 19.
This one?
Yeah, you calculate the friction force on the edges of the plunger, I assume?
Yes.
Intuitively, wouldn't the friction be larger when the French press is wet on the edges? Like, I guess from an intuitive perspective, it seems like when there's water on the edges of the press, it would be stickier, and that would somehow affect the friction force. So was the French press completely dry when you pulled the plunger up to measure the friction force?
Yes, so the friction force we did without any fluids inside, and we did make sure that it was completely dry and left it out to like sit the night before, and made sure that everything was in perfect condition before we took the video, because we wanted to kind of get rid of any extraneous factors that would mess with our calculation.
Intuitively though, wouldn't that create a different friction coefficient than with a wet press, which is what's happening when the fluid is in the press?
I would imagine that perhaps it would a little bit, but in the French press, when it's falling through a liquid, and our French press in particular does not completely touch this, like we chose specifically a French press that did not have an extremely large amount of friction on the sides, because we wanted to be able to do our trials wherein we added increasingly more and more mass to the top of the plunger. It made it easier for our analysis and conclusion. So we needed to calculate our friction, but it was small, it was very small, because it was not as big of a deal as drag when it's in the water. So I would imagine that it would be a little different, but would not drastically affect our conclusion.
Okay. But if you go back to the next slide, slide 20. And I mean, you mentioned that the friction force here isn't as relevant in your French press, but if you are underestimating the frictional force, wouldn't that create a larger estimate of the drag force at smaller Reynolds numbers than at larger Reynolds numbers, causing the decrease in the drag coefficient at lower Reynolds numbers?
Our Reynolds graph here, as I mentioned at the end, has a shift compared to that of the original Reynolds graph, because it was, created with spheres instead of a French press, which is a very different shape. So perhaps if it did cause our drag coefficient numbers to decrease, then the whole graph would be shifted down a bit. But nevertheless, we would still expect that it would that a French press would abide by Reynolds number.
Can you go to slide 18, please? I'm curious, you mentioned that you would take the standard deviation, that your hypothesis was that the standard deviation would increase linearly with Reynolds number. Did you have any sort of theoretical calculations that would imply that?
So we took the standard deviation of each of our velocity data sets, of which we had a lot of numbers, and then set that against Reynolds number, and we had expected that we would see an upward trend, but this obviously shows that we did not see kind of the trend that we expected we would. It's a little more chaotic, but I felt that it merited mentioning because that was our original hypothesis, and we had to kind of move beyond that. But yes. Did that answer your question?
I guess so. Do you have any sort of new theoretical basis for why the graph might look like this?
We did not touch upon that in our conclusion, but I would imagine that the reason that this did not work out is due to the unpredictability of turbulence. We redid our trials many times to make sure, each one, the 0 grams, the 10 grams, we took several videos for each and analyzed all of those to make sure that we had consistent calculations, because after having worked with turbulent flow for 12 months, it became quite clear that it was as unpredictable as everyone said that it was. And I would imagine that the reason the standard deviation Reynolds number theory did not work is partially because of the different shape of the French press that I mentioned, and also because of the just unpredictability of turbulence versus the fact that we use an average value for Reynolds number.
I guess moving, because you mentioned the geometry, moving back to that, do you have any sort of, even if you just touched upon it, explanation of how the mesh and the plunger geometry might affect your calculations as compared to a sphere falling through water?
I think that if we were to continue these experiments and move forward to further conclusions, it would be a good idea to take the area of the holes in the French press and subtract it from the total area of the metal plate, and perhaps work with that instead and see how it differs from the way that we did it. Because I imagine that it would be a little different because of that missing area. But you know, in a French press, the water is being pushed through those holes and then subsequently creating the eddies that cause turbulence. And yes.
Absolutely, that makes sense. Do you have any hypotheses on how that partial covering might affect even just factors like the velocity through the holes, that kind of thing?
Yes, because if you have like a constant amount of the fluid in the French press, we throughout all of our trials made sure that we had the same amount of fluid in there and that it wasn't changing, so that we could have our factors that stayed the same. And so I would imagine if you had that, but if you had like one metal plate and then a giant hole in the center, you would get a different sort of turbulence, or perhaps less turbulence compared to that of several tiny holes. Just because it's, you know, water that is being forced through, or a liquid that is being forced through that small space, but at the same, with the same downward force.
1 minute.
Can you elaborate on your theory for why one big hole might create less turbulence than a few little holes, since that would have a decreased length scale, which would technically imply a lower Reynolds number?
So, I think that it would eventually even out in terms of our Reynolds numbers, because as I mentioned, we used an average. I think that it would cause that having many small holes would cause a higher initial velocity, but that it would not create like a generally increased turbulence. And so with that kind of transition from higher initial velocities into laminar, that it would eventually average out to what we kind of what we found with our graph, since we used an average for Reynolds number.
Time. Thank you very much.
The reporter and the opponent now have 1 minute to prepare for their summary addresses. Your summary address is 1 minute.
Okay, time.
Okay. The opponent may now address the jury for 1 minute, giving a summary of your conversation.
First of all, I want to congratulate you on great work. I really liked how you focused on the Reynolds stuff. I would have liked to see a little bit more analysis on the mesh aspect, since if you take, for instance, just a solid metal plate and push it through water, that holds rough, that would apply more to the theory that you use than the mesh, since you focus mostly on the drag force and how that applies. without considering the mesh. And I think the mesh is what makes this problem really cool. And I also thought that with future work, it could be interesting to consider how friction force would be affected by the edges of the plunger and how water and how the wetness would affect that. So that's more of a minor note. I think, and I think
That's
the, oh, okay, cool. Congratulations again.
Thank you.
The reporter may address the jury for 1 minute, giving a summary of the conversation, and if appropriate, responding to the opponent's summary.
To begin, I'd like to summarize and say that we felt the French press acted and still reflected the same kind of properties and shape of Reynolds graph. However, there were shifts in the graph that could account for the different shape in the French press and the different turbulence that it causes. I do think that it would be very important to address in further experiments how the mesh and the different hole sizes that different French presses have could affect those velocity values, because they were so important and central to the project. And thank you very much.
Okay.
Thank you as well.
We now have 8 minutes for questions from the jury, so we'll this time start at that end if you guys want to start. Someone down there. If you don't have anything, we can.
Okay. I'll start. I don't know if this is a hard question. I'm asking because I don't understand myself. This is a question outside of my pay grade. So I've often heard that turbulence is related to the way that energy at large scales gets sent down to small scales. So for example, if I start with something with a velocity that's the same across the entire system, maybe in a turbulent system it'll turn into eddies at small scale. I think that's the idea. So energy starts at large scales and somehow gets distributed to small scales. Now maybe this is totally not relevant in the system that you studied, but I'm curious, do you think that that might be related to any of the data that you drew, or would you be able to draw that conclusion? And if not, maybe do you have any ideas of how you might probe such physics?
Yes, I think that it is related, because knowing the setup of our particular experiment, we had our French press, and then the handle, we taped several weights to the top of it and varied that throughout the trials. That of course starts as gravitational energy, and I would imagine that that is transferred as the plunger is sent down, and thus creating those eddies and the wild velocities that you see in turbulence.
Thank you.
Sure. This is a question for, I guess, both the reporter and the opposition. The opposition had talked about the difference between the frictional force when you use the plunger as both dry and when wet. But do you feel like there would be a bigger difference to consider the difference in the pressure contained within that kind of piston between the when you did it in both air and in the water? Would that have led to a bigger difference in how you measure the friction?
That is an excellent question. I could not say for sure, because we did not explore that in our particular experiments, but I would imagine that perhaps it would be a little bit different, and that would be a good, important thing to consider going forward in experiments and in calculating friction for our French press.
An opposition, do you feel like the pressure would be a bigger difference in what you talked about with the wet versus the dry?
Air, I guess, is also a fluid, but it's compressible, whereas water is mostly incompressible.
Mm-hmm.
So there are very different properties there, but given that the air drag, at least I would imagine the air drag would be pretty minimal. So it's pretty similar to working in a vacuum.
Okay.
So I don't think and water is incompressible, so the pressure isn't really as important there.
Mm-hmm. Okay.
That's just my
A
intuition.
question for the reporter. It went by, I mean, you had it up there long enough, but you had the slide with the 3 videos with 0 weight, 30 milligrams, 30 grams, and 60. Did I see that the 30 milligram weight actually went down more slowly than the 0?
So the 30 in the middle, I
Right.
should have mentioned this in my presentation, but it's actually glycerin, not water. The two on the outside, the 0 grams and the 60 grams were both water, and so they fell much faster. The 30 grams in the middle was one of the glycerin trials that we did.
With a heavier drag.
Yes, it would have been
Okay.
much slower. Yes.
Okay, good. If I could just continue, Cary. Yeah. The original Reynolds graph was, it looked like it was log. Did I see that right? And then you would switch, you had some of your graphs where the x-axis, where the Reynolds number was, changed to linear. Was that intentional on your part for wanting, what you wanted to display about the variation of the points?
So I have actually created both graphs. I chose to put the non-log graph in for our original spheres because it was what we created in our original experiment when we were first learning about Reynolds' graph, and we just had not thought, I guess, about putting the log on the axis, but I have done it myself and seen what the shape looks like. It's very similar, it's just kind of compressed a little bit more because it's easier to visualize without the large numbers on the x-axis, but it is still a very similar shape.
Okay.
You guys down there, do you have a question?
Yeah, so question to the presenter. So in terms of this drag coefficient, or I guess the drag forces in general, do you expect these to be sort of like, you sort of are attaching a single drag coefficient, it seemed, for each trial. Do you expect this to be like a single sort of homogeneous property within the French press, or would you expect any variation maybe within the French press, maybe with time or where it is within in the water?
So we recalculated our drag coefficient for each trial because, of course, we varied the mass on top as well as the substance inside the French press, and so we knew that some of the factors, like for example the constant velocity region of the plunger, were going to be different for each trial. So we recalculated it and did see variation, which is how you get the shape on the Reynolds graph where it goes from very high drag coefficient to lower drag
I suppose
coefficient.
I mean within like a single trial, like within like say near the edge of the French press versus the center. Do you expect the same drag coefficient for each location?
The way that we modeled this particular experiment using the way that we modeled our French press when creating our calculations, I think we assumed that it would be the same, but perhaps in a real life situation where there was more ability to account for the holes in the French press as well as the mesh, that it would change a little bit.
I have a question. Oh, did you have a question?
Oh, yeah.
Go ahead. Go.
So I think in your updated Reynolds graph, in the end, where you have one data point on the far left and a cluster on the right, I remember you said that something like you expect the cluster on the right to sort of, as an evidence of reproducing the theory graph that you're expecting, this little curvy behavior at the end. How could you come up with such a conclusion where there's no data points in between? Why can't that just be a linear relation between the cluster and the one data point?
So we do have we had more data points that continued up off the graph, but I chose not to include them because it changed the scaling. Because as you get further and further into Stokes region with Reynolds numbers between 0 and 1 and gets closer and closer to 0, the drag coefficient gets extremely high, and it compressed our graph so much that we were concerned about that it was not highlighting what we wanted to highlight on that particular slide, which is that we were able to replicate the kind of curvy behavior that you see on the right side of the Reynolds graph. But we did see in those points that it continued up in the fashion that we expected. We had trouble replicating Reynolds number values from in the gap portion that you saw on the graph, but if you were to extend that the x-axis out in terms of orders of magnitude, you would see a better representation of the Reynolds graph.
And time is up.
Thank you very much, everyone.